Okay, so this is 15.7, optimization, essentially, or the first of the two optimization sections. 15.8 will be as well. 15.8 will be a special technique that's kind of unique to multivariable calculus as opposed to single variable, but we'll talk about that when we get there. Okay, so 15.7 is the one that's more directly analogous to the optimization sections in one variable calculus. All right, so what's the problem? The problem is we have a multivariable function, for example, f of x comma y. Everything we talk about can be, we're going to do examples mostly in two variables, but everything we talk about can be extended to as many variables as you like in pretty obvious ways. Okay, so we have a function f of x comma y. Let's draw a graph. So here's my function. We have a region that we're interested in terms of the domain, right? So we're interested in inputs to our function, let's say, only in a particular region. So let's say only in here, right? So for whatever application we're doing, we're only allowed to have x and x comma y inside this rectangular box as our inputs. Okay, so what we want to do is we want to find the biggest and smallest values that f achieves forward inputs within that box. All right, so in terms of a picture, perhaps we go up to here, and then maybe the box looks like, when we push it upstairs, it looks something like that, right, on the graph. And so we're looking for the highest point. So perhaps in this picture, it looks like it could be like something there, and maybe the lowest point, maybe something there. All right, so we're looking for the highest and lowest points that our function achieves inside our box. Okay, so just like, so let me actually write down the problem. So find biggest / smallest values that f of x comma y achieves in the region R. I guess in this picture, this rectangular box would be R. And I want to emphasize R is a region that's in the plane, in the domain. Okay. So this is our the main problem that we're going to be focusing on in this section. It's exactly like the one variable calculus problem. Find biggest, smallest values that f of x achieves in the region or in the interval in one variable calculus, right? I guess we'll just call it I in R. Okay, it's directly analogous to this problem. And the technique that we're going to do today is going to be directly analogous to the technique that we used in one variable calculus. Okay. All right, there will be some complications. And then there will be a special technique, like we said, unique to multivariable calculus that we'll talk about in 15.8. Okay, but that's the general idea of what we're trying to look for. And kind of our inspiration for our technique is, again, one variable calculus. All right, and again, I guess I should draw the one variable calculus equivalent picture, right? So here's my function, and in this case, my region interval is just going to be from here to here, and we're looking for the highest point. Maybe it looks like it could be that one, and the lowest point within our interval. Okay, before we actually start to do anything, let me do some preliminary definitions and stuff. It'll be exactly the same ones as in single variable calculus. We're not going to dwell on them. I want to spend almost all the time in this section on actually solving the problem. Okay. All right, but again, we need to have some sort of definition. So I'm just going to actually list them, say a few words about them, and we'll pretty much gloss over completely the official mathematical definitions of all of them. All right, but you can maybe even figure them out yourselves just by doing the analogy between multi and single variable calculus. So local max, maximum, local minimum, right? absolute max mins, right? So those are the two kind of concepts that you talked about in single variable calculus. They directly translate to multivariable calculus. All right. So a local maximum or minimum is a situation. So let's say local maximum is a situation where you have a point, and its output, when you plug it into your multivariable function, is the biggest it can be in a neighborhood, in its neighborhood, right? So maybe the function looks kind of like that, right? And so this function, at this point, the function is in its neighborhood as big as possible. All right. Minimum, same idea. All right. So it's hard to draw a two-variable picture, but it's directly analogous to this situation in single variable calculus, where you have this point right there is a local max. This point right there gives a local max. This point right there gives a local max. All right. So there you can see they're top of hills, and that's the same idea as in multivariable calculus. You want to think of these as being the top of the hills for the maximum and bottom of hills for the minimum. Okay. All right. What's important about this is, of course, that we know in single variable calculus, when you do optimization, you actually often, as in the problem we talked about above, you actually want let's say the absolute maximum, the biggest value that your function achieves. And so that would be right there. But in finding this guy, you're going to find the local maximums and minimums as you work through the process of finding critical points. Okay, so it's going to be the same idea in multivariable calculus, where we oftentimes just want the absolute biggest or absolute smallest value that our function achieves and where it achieves it. But we're going to often find local max and mins as we work through the process. Okay, I guess I kind of already mentioned it, but absolute max is the absolute biggest value. Okay, so in terms of this kind of multivariable picture, which is, again, very hard to draw, but let me draw something like that. Let's say there's another hill here. The first hill here, that's a local max, but not an absolute max, because this other point over here is even higher. Okay. All right. So local max min, biggest or smallest in your neighborhood. Absolute max mins, biggest or smallest value overall in the region that you're interested in. Okay. All right. So what was the strategy in single variable calculus for finding absolute max and mins? Well, we had an interval that we're interested in single variable calculus. We have our function. We said that if your tangent, if you're at a maximum, right? If you're at an absolute maximum, let's say we're looking for absolute maximum. If you're looking for absolute maximum and you're at a point which is exactly the absolute maximum in the interior of the interval, interior, not the endpoints, then if your function is differentiable, then the tangent line at that point has to be horizontal. All right. So at interior max or mins, tangent line is horizontal. Okay, and that was basically the key point that you need in single variable calculus to be able to find absolute max and mins, because, well, where's the tangent line horizontal? That's going to be where f prime is equal to 0. Okay. All right. I also mentioned that interior tangent line is horizontal if f prime exists. Okay. All right. So this leads us to a strategy of finding absolute max and mins. The strategy is to, 1, find points where f prime equals 0, right? Because if you have an interior max or min, it has to be at one of these points as long as your function is differentiable there. So these are, I guess I should put a little title here. These are my candidates. These are my candidates for the max or min, right? They're going to be points where the f prime is 0. So in this picture above, you're going to be looking for this point, this point, this point, this point. You're gonna find these points, all right? And again, of course, you're not going to have a picture, so you can't literally instantly say that this guy's right here is the absolute max, right? But the deal is that the kind of useful feature of this is that the points where f prime is 0 is often going to be very, very finite, right? Or literally finite, or maybe even just a few, right? Maybe just 2 points or 3 points. So immediately you can see this is great, because if I just tell you, I have a function, I want you to find the maximum value within this interval, and I give you, just a formula for the function, you have no idea what it looks like, right? Where could the absolute max or the min be? It could be anywhere, right? It could be anywhere within this interval. So it's an infinite problem in a way, right? The possibilities are infinite. But now that we understand the derivative, you know that the max has to happen in the interior. If the max is in the interior, it has to happen at a point where f prime is 0, or where it's not differentiable. And so immediately you've cut down your infinite problem into just a few, right? Sorry, let me mark them in the domain. So maybe here, 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 and here are your critical points where f prime is 0. So from an infinite number of possibilities to just a finite, just 4 possibilities in the interior. Okay, so this is the real power of the technique from single variable calculus. Okay, so these are my first set of candidates. Number 2 is going to be endpoints, right? And the reason for that is because at the endpoint, if you have a maximum or minimum at an endpoint, absolute max or min, it does not have to satisfy f prime equals 0, because your function could look like this, right? Here's the region of interest, and the absolute maximum is right there, right? And it's not where f prime is 0. So calculus, in a way, we can maybe say it like this: calculus can only capture absolute max and mins when they're in the interior of your region. All right. Okay, so that's why we need this separate point, number 2 here. Okay, in one variable calculus, this was not a problem, because endpoints, how many endpoints do you have? Well, if your interval is just one piece, there's only 2 endpoints. So not really a big issue. All right, number 3 is going to be where f prime does not exist. Right? And of course, you have to consider this, because where f prime does not exist, of course, is not going to show up when you look for f prime, when you solve f prime equals 0. Right? And you do need to include number 3, because, well, you can have a function with a v, right? Here's our region of interest. If you just solve for where f prime is 0, you're not going to capture this point right there, because there is no f prime there, right? So that's why we have to also consider number 3 as a separate point. All right. Okay, so that was a super quick review of single variable calculus. Before I actually move on to multi, what do we do after we get all these candidates, right? These are my candidates. So maybe there's 5 points from step 1, 2 points from step 2, maybe 1 point from step 3. What do I do with them? Well, if I want the absolute max or min, I just plug in all those candidates. If I want the max, it's going to be the biggest among those candidates. The min is going to be the smallest among those candidates. And that's because we know for sure that the absolute max and min have to be among those candidates. All right? Okay. Multivariable. How do we do it? Pretty much the same idea. All right? Number 1 is going to be find where tangent plane is horizontal. Okay, so in single variable calculus, we looked where f prime was equal to 0, and that was because f prime equals 0 is where the tangent line is horizontal. And again, the entire motivation here is if you're at a maximum or a minimum, absolute max or min in the interior where you're differentiable, then your tangent line has to be horizontal, right? Maybe I say it like this. if you're at an interior point right there, and your tangent line is like that, right? Then for sure you're not at a max or min, because just previous to this point, you were a little smaller, and just after this point, you were a little bigger. So you're definitely not at an absolute max or min, right? So that means the only possible way you could be a max or min in the interior is where f prime is 0. Okay, so it's literally the same idea here. In multivariable, you want to find places where the tangent plane is horizontal. That's actually that's the visual version of this, but the kind of computational version is find where the directional derivative of f in the direction u is equal to 0 for every u, right? So you want to look for points where you take the directional derivative in any direction, and your function is kind of stationary, right? Horizontal. Okay. So in terms of the picture, we're looking for points, you know, kind of like this, and the tangent plane here is horizontal. All right. Let me continue with this line of thought here. Find where duf equals 0. And what is d sub u of f, the directional derivative? That's gradient f dot u, right? So that's going to be find where, let me write the full words, find where gradient f dot u equals 0 for every u. Okay. All right, so this is equivalent to finding where the tangent plane is horizontal. And computationally, we're going to be doing essentially this. But we're going to take one more step. If the gradient of f, we're looking for points at this moment where gradient f dot u is equal to 0 for every direction. Okay. What vector, what does a vector have to be so that when it dots every other vector, it's equal to 0? Only the 0 vector can do that. All right. So this is the same as saying gradient f itself is 0. All right. So luckily for us, we don't actually have to work with the directional derivative directly, right? We just work with the gradient. Okay. So essentially, we're just looking for points. At least the equivalent of step 1 is we're looking for points where the gradient f is equal to 0. And that's a nice kind of compact way to say it. In practice, that means you're going to have to solve f sub x equals 0, f sub y equals 0. Both these equations simultaneously. All right. So you need to find points a comma b where f sub x of a comma b equals 0 and f sub y of a comma b equals 0. Okay. So this is where the kind of difficulties come in, because you're going to be solving algebra problems where you have multiple conditions, multiple equations. All right. And these are going to be oftentimes non-linear problems. So there isn't a set algorithm for solving these problems. Every problem is kind of ad hoc. You use whatever technique you can to solve the algebra. Okay. And of course, in terms of if we have a multivariable function with more than 2 variables, then you would just, it would be the same idea up to this point, gradient f equals 0. And then kind of in terms of your actual computations, you would be solving f sub x is 0, f sub y is 0, and then f sub z is 0. And then f sub w is 0 if there's a w, or so on. No matter, it doesn't matter how many number of variables. All right. Okay. And I always like to say this, right? Philosophically, let's go back to two variables, the 2 variable setting. What are we solving? We're solving a problem where we have 2 equations, right? F sub x equals 0 and f sub y equals 0. We are in R2, right? We're in the plane, so there's 2 unknowns. So generally, there's going to be a finite number of solutions. Okay, so that means that generally, this is kind of a good problem to solve in that you can actually do it. All right. Again, always in general. This is in general. There's always going to be exceptions. Okay. So that's number 1. Number 2, we said was for the single variable calculus situation was we had endpoints. And we said the minimum or the maximum can always possibly occur at the endpoints. Same idea here. in multivariable calculus. You can have a function, let me try to draw something like this. Let's say you're interested in this region here, right? And again, here's another complication. So in part one, in kind of step one, we see a complication that we have to solve what can be pretty unpleasant algebra problems. And again, in single variable calculus, it was just one equation, right? You just have f prime equals 0, so it was a lot easier. Now you're going to have to solve a two equation, two unknowns. All right, so that was one complication. In two variables, the complication is that the endpoints, in quotes, is much more complicated, right? If we're interested in this region, right, we're interested in a region as opposed to just an interval. In one variable calculus, the kind of boundary where we can't use calculus to understand it was the two endpoints, so just 2 points. But now you can, if you look at this picture, what's the boundary? The boundary is actually this segment, this segment, this segment, and that segment. So solving where gradient equals 0, gradient f equals 0, is not going to capture any maximums or minimums of your function above this boundary. All right, so for example, if I have a function that's maybe, let's just draw something kind of simple, just a function that's kind of curved upwards like that, right, above this square here. Okay, so here you can kind of see the minimum is going to occur somewhere along this this segment, and the maximum is going to occur along this segment, right? And in between, it's kind of always going upwards, so there's no point where the gradient is 0. Right? So if you're only looking for points where gradient is 0, you're not going to find any, and then you might say there's no solutions, but then you'd be terribly wrong because you didn't check the boundary. Okay, so instead of endpoints, now we're going to say the boundary. You have to check the interior, which is step 1, right? And then you have to check the boundary, which is step 2. Okay, we'll talk about how to deal with that. Again, it's a major complication compared to the boundary in one variable calculus just being 2 simple points. Okay, but we'll get to that when we actually do our example. Step 3 is where f prime does not exist, f not differentiable, right? And there's not much to say there. We're not going to be working, like I said, with functions which are horribly not differentiable, but you know, we might have a function that looks like f of x comma y equals square root x squared plus y squared, right? What is that? That looks like a cone, like this, x, y, z, and its absolute minimum. Let's say we're interested in this region here, right? Its absolute minimum is going to be at the tip of the cone, but the function is not differentiable there. You're not going to capture that point just by looking at the gradient. All right. So for our class, where f is not differentiable is generally going to be pretty obvious in that you're going to take the derivatives of f. You're going to take f sub x and f sub y, and you'll notice that at 0, 0, right, you're going to be dividing by 0, and that's going to be for our class again where we're not differentiable. So it's going to be places that are pretty obvious. We're not going to play with any really tricky functions in our class. Okay, but always keep in mind that this can happen, right? Because literally this is one of the most simple of functions, this cone, and already it has a you'll fail the problem if you don't take this into consideration. Oh, by the way, so the one variable version of this was just the absolute value function, right? F of x equals absolute value x, right? If you try to only look at where f prime is 0, and you don't think about things too much, you're going to miss that. You're going to miss that kind of corner there. Okay, so that's our strategy. Let's actually do a problem. So actually, before I actually do the problem, if you think back to one variable calculus, you also maybe remember some other stuff. Perhaps you used a second derivative test to work in optimization problems. We will talk about a second derivative test in a few minutes here, towards the latter part of this section. But I would recommend never using the second derivative test when you're doing these kinds of optimization problems, because, or the equivalent of the second derivative test for multivariable. I don't even recommend you to do it in one variable calculus, because why bother, right? You find where f prime is 0, you get 3 points in one variable calculus, let's say. You have the endpoints, which is 2 points, and let's say you have 1 point where you're not differentiable. So you've got 6 candidates. You know for a fact your maximum or minimum is within those 6 points. So you just plug those into your original function. Whichever one's biggest, you're done. Whichever one's smallest, you're done, right? Why bother with the second derivative test where you have to take the second derivative, do some evaluations, remember what the second derivative test actually says? Waste of time, in a way, right? Because all you have to do is plug in points, plug in your candidates. So I would never recommend doing the second derivative test in the kind of problems that we'll mostly be seeing. Where is the second derivative test useful? It's mostly useful in theory. When you're studying, for example, differential equations, where you actually don't even have an equation for your function, but yet you're still looking for max mins or something like that, then you have to kind of analyze around the fact that you don't have an equation. And so you have to use properties such as the second derivative test properties in order to get some understanding of the function. All right, so for the kind of computational examples I'm going to do, I'm not even going to consider the second derivative test. And in fact, you'll notice I'm not going to even teach you the second derivative test before doing these examples. All right, so here's my example. So I want to find biggest and smallest values. I guess I should find the biggest, smallest values that f of x comma y equals xy squared minus x achieves in the region, in the, let me give it a more accurate description, in the triangular region bounded by, let's say, minus 1 comma 0, minus 1 comma 2, and 1 comma 0. Or not bounded by, triangular region with corners. All right. Okay, so this is a very typical optimization problem. We'll be seeing word problems. There are definitely word problems in this section. And for those, you just have to analyze just as you did in single variable calculus, right? You read the words. If you see kind of the words biggest or smallest, you see the words fastest or slowest, farthest or closest, right? That means you're almost certainly thinking about a optimization problem. And then you have to think about, okay, what is the function that I'm trying to find the biggest and smallest value of? So that would be equivalent to the f of x here, right? And which values am I allowed to be considering? And that's going to be the region of interest, and that's going to be equivalent to this triangular, or this description here of the region of interest. All right. Okay. So let me draw a picture, at least of the region. It's pretty useful to be drawing pictures here, just to be able to see what's going on. So we have a triangular region. So here's x and y. And again, these regions always live in a domain, right? So triangular region. So we've got minus 1 comma 0 here. We've got 1 comma 0. And we've got minus 1 comma 2. Right? And we're interested in the triangular region with these three as the corners. So we're interested in this region right there. Okay, so we're trying to find the biggest and smallest values that f of x achieves for inputs within this region. Okay. All right, so let's do part one, which was so our book. Just a bit on kind of terminology. So our book calls critical points where gradient f is 0, where the derivatives are 0, where all the directional derivatives are 0, or where the derivatives do not exist, right? But I think a lot of calculus books call critical points just only where the derivative is 0. So I'm just going to call number 1 where gradient f equals 0, all right? And just avoid the whole idea. But just be aware that sometimes there's the terminology is different from book to book. Okay, gradient f is 0. Oh, by the way, of course, we're only working with functions that are pretty much differentiable everywhere, right? We've said this actually already. So where the directional derivatives equal 0 is the same as where gradient f equals 0, because everything is differentiable, and so functions can be approximated by a tangent plane and so on. All right. Just want to make sure I get the technicalities out of the way. Okay, anyways, where's gradient f equals 0? So my function was xy squared minus x. So this part, in terms of the procedure, is relatively straightforward, right? You just take the derivatives. F sub x is equal to y squared minus 1. F sub y is equal to 2xy. And now you need to solve y squared minus 1 equals 0 and 2xy equals 0 simultaneously. All right. So again, a system of equations. That's a 0 there. Okay. And depending on the structure of your function, depending on the formula for your function, this system of equations here could be really hard. It could be really easy. It could be that you could solve one equation first and then immediately solve the second one, or it could be mixed. It could be really hard. All right. So just be aware the algebra can vary from super easy to super difficult. All right. This one is not too bad. I need to solve both equations at once. I look at the first equation. Let me label these. I'm going to call this A. I'm going to call this B. So I can see that equation A immediately tells me that y squared is equal to 1. All right, and so that immediately tells me y is plus or minus 1. Okay. Now again, you could if I just even change this function just a little bit, this system might be a lot harder than this. All right, so we're just in a way lucky that this first equation immediately just gave me y. All right, so you definitely need to be very comfortable with your algebra of solving multiple equations and multiple unknowns at the same time. Okay, in any case, y has to be plus or minus 1. Okay, so that tells me that for b, right, whether y is plus or minus 1 doesn't matter. That means that 2x times, well, y has to be 1 or minus 1. So let me actually do it a little kind of carefully. 2x times 1, this is the case where y equals 1 equals 0, right? This is where y equals 1. And immediately that tells me x is equal to 0, right? And what about when y is minus 1? Well, 2x times minus 1 equals 0, and immediately also x equals 0. Okay, so in both the two cases, I have x equals 0. And so what that means is gradient f equals 0 at 0, 1 and 0, minus 1. Okay, so that's our candidates for my maximum or minimum within my region, right? Within the triangular region, in the interior of the region. Okay. And of course, in terms of the picture, these 2 points are where the tangent plane is horizontal. Okay. Oh, by the way, in single variable calculus, you can have the tangent plane be horizontal, where your function looks like that, right? Which would be like a local max. You could have it be horizontal where it looks like that, local min. But you could also have it be horizontal where it looks like that, right? Y equals x cubed, where it's neither local max or min. Same thing can happen in multivariable. Local max could be, kind of like the top of a hill. You could have this at the bottom of a pit or something. And then the situation with Neither is, we've kind of seen this already, is like a saddle, right? Tangent plane right there is horizontal, but in this direction, you're going downwards, but in that direction, you're going upwards, right? In this direction, you're going down, that direction, you're going up, and so it's neither a max nor a min, okay? So definitely, just because gradient f equals 0 doesn't necessarily mean you're a local max or min, all right? It could be the neither situation. All right, in any case, we're going to continue here. That's it for part 1. So now into part 2. Part 2 was the boundary, right? And remember, this was analogous to looking at the endpoints. And in single variable calculus, the endpoints, no problem, right? But now the boundary of our region, where part 1 of this problem, where step 1 of this problem cannot do anything for us, is this region, right? Because again, your function could increase as it hits the boundary, and calculus isn't going to capture that with gradient f equals 0 there, because it might not be. So the boundary here is quite complicated. Oh, sorry. I should have said something up here. 0, 1 and 0, -1 was our two candidates, but our region of interest is in this triangular region. 0, -1 is somewhere down here, right, in the negative y, underneath the x-axis. And so 0, -1 actually is not in our region, so we always remember to toss it out. All right. Okay. Certainly, we don't want to answer which is not even in the region that we're interested in. Okay. So our boundary actually is quite complicated. So the question is, how do we deal with this? Well, luckily for us, we learned vector value functions and parametrization, and we immediately noticed that our region consists of three obvious curves, right? There's a line segment from here to here, there's a line segment from here to here, and there's a line segment from here to here, right? So if we think of our function, so above these line segments, right, in terms of the graph, right, so maybe we're looking at a triangle like, triangle like this, right? Above our function, above this region, right, our function maybe looks like that. And our triangle goes up to maybe something that's, of course, curved, something like that, right? Well, if we just look, for example, in this line segment, we're upstairs, it's going to look like that, right? And so what we're doing is we're just looking at a single variable problem, okay? Inputs down here along this line segment, outputs up there along that curve over there, right? So it's a single variable problem. So what we're going to do in order to solve these boundary problems is we're going to convert them into single variable calculus problems. And then we'll solve the single variable calculus problems as optimization problems themselves, all right? So what we're going to end up doing here is we're going to be doing 3 mini optimization problems, 1 variable calculus optimization problems. The first mini one, let's say, is going to be this one. The second one is going to be this segment, and the third one is going to be that segment. All right. Because our region here is naturally composed of 3 segments, we're going to have to do 3 problems here. Okay. All right. So how do we do this? Well, we parameterize the curve. So let's do number 1. So do optimization problems. Because why optimization? Well, we're looking for ultimately for the biggest and smallest values of our function. So where can that happen if it's on the boundary? It's got to be where the function is biggest or smallest at each of the boundary segments, right? Those are going to be the candidates. So do optimization problems on 1, 2, and 3. Okay, and again, in this 2 variable setting, f of x comma y is our function. Our boundary is going to be a curve, which is 1-dimensional. So essentially, you're always going to be ending up with a 1 variable calculus problem, or several 1 variable calculus problems. What happens if we have 3 variables, f of x comma y comma z? We'll deal with that later. It gets a lot worse. Okay, So segment 1, let me write down coordinates for my region here. So this was 1, 0. This one was -1, 0. And the last one was -1, 2, right? So the first one is going to be the segment from 1, 0 to -1, 2. All right. We're going to parameterize this curve and then convert to a one variable problem. So parameterization. So line segment, so the easiest is we need a point, and let's just use 1, 0. We need a direction, right? So if we're starting at 1, 0, we want to go from 1, 0 to -1, 2. So my direction is going to be, let me use the vector. I'm going to take 2 minus 0 is my y coordinate, and then -1, -1 minus -1 is going to be my x direction, so -2 here. My direction is going to be a vector. Let me use sharp brackets. There, all right? So my parameterization is going to be x of t equals 1 from that 1, 0, plus, minus 2t, right? Minus 2t because of that -2 in the direction vector. And y of t is equal to 0, and then plus 2t. So just 2t, all right? Okay, so if we compose our function with this parameterization, in other words, we look at f of x of t, comma y of t, right, which is f of 1 minus 2t, comma 2t, right, that's a one variable calculus function, right, with the only variable being t. Okay, so that's why we have a one variable calculus problem. And again, in terms of the picture, what we're doing is we're only looking along this line segment, and we're figuring out, or we're going to be in 1 second, figuring out where the function is the biggest it can be and the smallest it can be, or candidates for those within the region, above this interval. So that would, in this picture, be perhaps that point right there where you have a flat tangent line. Okay. All right, so we want to solve, so our f prime is 0, right? We want to solve f prime is 0. So when d dt f of 1 minus 2t, comma 2t equals 0. All right, I don't like how I wrote this. I'm going to write solve f prime of t equals 0, right? Which means solve d dt of this equals 0. Okay. All right. Oh, by the way, I should for sure mention we're going from with this parameterization that we chose, t is between 0 and 1, right? You always need to know the interval of interest because well, we need to toss out any candidates that we find that are outside the interval of interest. But also, number 2, we need to consider the boundaries, the endpoints, right? Okay. Oh, and probably a good idea always just to do a quick check, right? Did we do this parameterization correctly? When t is 0, I look at my parameterization. I get 1 minus 0, comma 0, which is where we were supposed to be. And then when t is 1, I get -1, comma 2, which is exactly where we're supposed to be. So our parameterization looks correct. Okay, for linear parameterization like this, you just need to check 2 points. Okay, by the way, this is my choice of parameterization. Any parameterization will do, any parameterization of this line segment will do. But of course, if you do a different parameterization, your endpoints might be different. All right, so it might not be 0 to 1. And we'll see an example of that when we do the next 2 steps. In any case, let's do our one variable calculus problem, right? So d dt f of 1 minus 2t, comma 2t, that's going to be the same as d dt of, and I'm just going to write out what this function is in terms of one variable. Our function was, let me write in the corner here, our function was f of x comma y was equal to xy squared minus x, okay? And so if I convert that to t's, this is going to be, x is now 1 minus 2t, so it's going to be 1 minus 2t. What's the best way to write this? Let's not go do fancy. Let's just brutally do this, right? X y squared minus x, 1 minus 2t. Okay. So I want to solve where this guy is equal to 0. Okay, so now you can literally see this is one variable calculus. The only thing that's happening here are t's. All right. Okay, by the way, you could do it this way that I did it, just change everything to t's. You could also use the chain rule to calculate this up here, because we've already calculated f sub x and f sub y. So the chain rule will tell you what this derivative will be. Do it whatever way you like, but that works perfectly as well. All right. Okay. So this is equal to what? And here is just brutal calculation from one variable calculus. All right. So d dt, I'm just going to use the product rule. So 2t minus 2, sorry, times 2t squared, and then 1 minus 2t times 2 times 2t, and 2t, and then times 2. This should be a plus. Let's see. I'm doing the product rule, so that should be a plus right there. Okay. And then the derivative here is going to be just 2. Okay. All right, so again, this is just pure single variable calculus. And at this point, it's not even calculus anymore. It's just pure algebra. So hopefully won't make any mistakes here. So t squared, 2, 2, 2. So we've got 8t minus 16t squared plus 2 equals 0. So we're ending up with minus 24t squared plus 8t plus 2 is equal to 0. 12t squared plus 4t plus 1, sorry, minus 4t minus 1 equals 0. Can we factor this? Nope. So let's use the quadratic equation. So t equals 4 plus or minus root 16 minus 4ac, 48 over 24. And so this is going to be 4 plus or minus, I can pull out a 16 here, so 4 square root 1 plus 3. Oh, okay, over 24. So this is going to be 1 plus or minus 2 over 6. So this is going to be 1 plus 2. I'm going to get 1/2, and I'm going to get, I don't want to write like this. So t equals 1/2. T equals minus 1/6. All right. So those are going to be my critical points for this segment of our triangle. So we had 2 other segments. All right. Okay, let's see. We were interested in t between 0 and 1, right? Because outside of t between 0 and 1 would be this portion of the line and that portion of the line, which is definitely outside our region. Okay, so immediately we see that t equals minus 6 is not going to be good. And so we only keep t equals 1/2 as our candidate. All right. Now, what is t equals 1/2 in terms of our 2 variable problem? Well, we had our parameterization all the way up there. It was x of t is 1 minus 2t, y of t is 2t. So x of t was 1 minus 2t, y of t is 2t. And so t equals 1/2 gives me, well, I plug in 1/2 here, I get 1 minus 1, which is 0, and put 1/2 here, I get 0, 1. Okay, so this candidate from this portion of the problem is going to be 0, 1. All right. Okay, that happens to be exactly right there. Okay, and by the way, notice that in our part 1 of the problem, over here, 0, 1 was also a candidate. That's perfectly fine. In fact, you expect it, because if 0, 1 was a candidate and it lived from part 1, and it lived on the boundary, then it's definitely going to be a candidate when you do the boundary as well. You can think about that, but you definitely expect it. All right, and it's perfectly okay for that to happen. In fact, you're very happy, because ultimately we're going to have to be plugging in all our candidates, and because 2 of these candidates are the same, we're going to save a couple seconds in terms of having to plug in an extra value. Okay. All right. So I'm going to move on to the next segment of our region, which was sorry, let me scroll back up, which was number 2. Which was number 2 here. Oh, it didn't work. Okay, sorry. Which is number 2 here. Okay, now notice I'm skipping over. Also, the candidates have to be the endpoints, right? Actually, let me. What I was going to do is I was going to wait till the end to gather all the endpoints, but let me make it all complete, kind of in each little mini segment. So the endpoints are going to be 1, 0 endpoint, right? And minus 1, 2. And remember, you have to remember these two guys, because single variable calculus, what we did up here with this calculation, is only gonna capture what's going on in the interior of this line segment and not what's going on at the endpoints. All right, so we have to include those two guys as our candidate. All right, let's do number 2. So number 2 is this bottom line segment, and let me actually redraw the picture here. So now we're looking at this segment right there. We're not worried about that. We're not worried about that. My endpoints are, in this case, minus 1, 0 and 1, 0. So this is segment number 2. And you can see already that these problems are going to be quite tedious, but there's no escape. There's no escape from that. You have to consider all these separate parts, because the maximum or minimum could absolutely lie on any one of these parts. The interior, part 1, segment 1, segment 2, or segment 3, or the endpoints of each of those segments. Okay, so here we're going to do the same idea, convert to a 1 variable problem, which means we need to parameterize. And I could parameterize in exactly the same way. But again, like I said, you can parameterize in different ways. And so here I'm just going to be, I'm going to take a super easy, simple parameterization. My parameterization is going to be x of t equals t, y of t equals 0. All right. If I did the same procedure as I did above, my parameterization would be almost as easy. It would be x of t equals 2t, y of t equals 0. But here I can literally see, right, as t moves, I'm moving from here to here for t between minus 1 and 1. Okay. All right. So the rest of my problem is, again, I want to rewrite my function in terms of t. And my original function was xy squared minus x. And so now I'm looking at, in terms of just on this segment, I'm going to be looking at f of x of t comma y of t, which is f of t comma 0, which is 0 minus t, right, which is just minus t. Okay. All right, this is great news, because super simple, right? F prime is equal to minus 1. F prime equals 0, never. All right, So what that means is that there's no candidates from this line segment down here for our absolute max and mins, okay, for the interior. Now, again, we always have candidates where at our endpoints. So endpoints. And here's where you can see why I wanted to leave the endpoints for the end, because I'm repeating them, right? This second endpoint here, I already wrote down in part 1. So if I had just left them to the end, I wouldn't actually have to repeat so many times. But it doesn't matter, right? Ultimately, the number of points you plug in is still going to be the same. All right, and finally for part 3. So part 3 was this vertical line segment. We're not worried about that. We're not worried about that. Our endpoints were -1, 0 and -1, 2. And so I'm going to parameterize that. And again, I can just parameterize it using the same technique I used in part 1. Part 1 of this this boundary portion of the problem. And that's perfectly fine. In fact, it's actually good to just have one technique that always works, right? This line segment thing will always work. But again, let me emphasize that you can use different parameterizations, and let me choose the parameterization here, x of t, so I can see that this is a vertical line. X is constant, -1. So y of t, it goes from 0 to 2, so y of t is just t, and then I need t between 0 and 2, okay? All right. So f of x of t, y of t is equal to f of -1, t. And that's going to be, again, my f was, let me rewrite it. F of x, y is xy squared minus x. And so this is going to be -1 times t squared minus -1. So that's going to be minus t squared plus 1, which means t is, sorry, getting a little ahead of myself. F prime is equal to minus 2t. F prime equals 0 when t equals 0, right? T equals 0 is indeed inside my interval of interest, which is 0 to 2. And so that gives me my candidate when t equals 0, x of 0 is -1, y of t is 0. So my candidate is going to be -1, 0. All right. And again, in this particular problem, it happens that my candidate was one of the endpoints. Perfectly legal. Okay. All right. And again, this computation that we just did only captures behavior inside the interval, right? So we also have to include the endpoints, -1, 0 and -1, 2. And again, these are repeats, but it's okay to write them down, right? It's not gonna really harm us. Okay, that's it. What we do now is we just gather all the candidates that we found from all the different parts of our problem and plug them all in, right? Because the maximum value of our function has to be among those candidates. The minimum value of our function has to be among those candidates. So obviously the biggest one among those has to be the biggest value, and the smallest among those has to be the smallest value. Okay, so our candidates were 0, 1, that was from part 1 of the problem. We had, sorry, let me go look up there. So we had, oh, and I guess the rest of the 3, yeah, and then we only had the three, ultimately we only had the 3 vertices of our triangle. So they were -1, 0, -1, 2, and 1, 0. All right. Okay, because we had a whole bunch of repeats. All right. So we just plug them all in, right? So this is why I hate even discussing the second derivative test kind of for these problems, because why should I do the second derivative test to determine whether these are max or mins when I'm going to get all the information I need just by plugging in right now, right? F of 0, 1, again, I should write down f of x comma y is xy squared minus x, right? So f of 0, 1 is going to be 0. F of minus 1 comma 0 is going to be 1. F of minus 1 comma 2 is going to be minus 4 plus 1, which is minus 3. And f of 1 comma 0 is going to be minus 1. All right. And so what is the biggest value my function achieves in the region, in this triangular region? There. All right. It's going to be 1 is going to be the biggest value. And it's achieved at minus 1 comma 0. The smallest value I achieve is minus 3. And that's going to happen when I put in the inputs minus 1 comma 2. All right. So max at minus 1 comma 0, value is 1. And min at minus 1 comma 2, value is negative 3. Okay. All right. So lots of computations, a lot of work, but ultimately, in terms of the procedure, it's very algorithmic. Every step is very well defined in terms of what you have to do. It's just that some of the steps are a little long. Some of them you have to kind of work the algebra a little carefully, but ultimately relatively straightforward. Okay, so hopefully that's good. Let's do a second example. All right, so my second example is going to be find the rectangular box that holds the biggest, has the largest volume. Oops, sorry. Given that, I guess, let's see. The sum of its dimensions is 120. So let me just draw a picture so I don't have to write all of it down. Given that, so let me call this x, let me call that y, let me call that z. Given that x plus y plus z equals 120, let's say. All right. Okay. So it might seem silly that you asked this, but I believe if you send a package through the USPS, how much you pay is calculated roughly by a calculation something like this. I think maybe they put more emphasis on the largest two dimensions. So it could be something like 2x plus 2y plus z or something like that. But roughly the same idea. All right. So a pretty practical problem. Okay. Let's see. The function that we want to work with is the volume, right? And it depends on x, y, and z. So volume is x, y, z. We're talking about a rectangular box, right? Now the question is, so it looks like on the face of it, maybe we have a 3-variable problem, right? X, y, and z. But the issue is that we have this kind of restriction here that x plus y plus z is 120, right? And what that does, at least for today, for 15.7, what that does is it effectively makes it so that we have a 2-variable problem because 2 of these variables can be written as a third, in terms of the third, right? So for example, I can write z is equal to 120 minus x minus y. And so z is not really a variable as it depends on x and it depends on y. Okay, at least that's the point of view we'll take today. For 15.8, we'll be able to solve this problem natively in 3 variables, which is really cool. Okay, but for today, we're going to have to do it this way, all right? Now, this is, before we actually continue here, this is completely analogous to those problems in one variable calculus where you had a fence, right? X and Y. You want to find the largest area, let's say, X times Y. And let's say there was a restriction on the perimeter, right? So 2X plus 2Y was equal to, let's say, 20. Okay, so what did you do there? Well, you said, you did exactly the same thing, right? So X plus, this tells me X plus Y is equal to 10, which tells me Y is equal to 10 minus X, which tells me A is equal to X times 10 minus X. And in one variable calculus, you could then start to do the problem because now A can be written as a one variable calculus problem, one variable function, okay? So that's literally what we're going to do up there with our problem. But I wanted to write this down because there's a little more we can get out of the one variable problem. So this is a practical problem. We're building a fence in the one variable problem. We're constructing a box in the multivariable problem. And so it's a physical problem. And so we have actual physical constraints here that X is bigger than or equal to 0, Y is bigger than or equal to 0. All right. Okay, X equals 0 means that we have a box which, for example, here we have a fence which doesn't enclose any area, right? X equals 0 means I'm kind of building a fence which is one segment like that and another segment right next to it. But let's not worry about that too much. Obviously, that's not going to be the minimum, or the maximum doesn't matter. Okay. So let's just leave it as X bigger than or equal to 0, Y bigger than or equal to 0. Well, for my one variable problem, I have a function, but I need to know what range of X I'm interested in, right? Well, I know I want X bigger than or equal to 0, literally says right there, okay? But I also have a range on the other side because Y bigger than or equal to 0 tells me, Y bigger than or equal to 0 tells me what? Well, Y is equal to 10 minus X, Y is bigger than or equal to 0, and so 0 is less than or equal to 10 minus X, and so X is less than or equal to 10. Okay, so that's what told me that I needed to consider X between 0 and 10. Okay, now I could, in one variable calculus, I could do the problem. I have a function and I have a region. Okay, so now in our multivariable setting, we're going to do literally the same thing, and we're going to get our region in literally the same way. Okay, all right, and I think this is a very good way to figure out the region. Otherwise, you have to do a lot of reasoning, and you can always easily mess up there. But the way I'm doing it here, there's no reasoning, right? The only reasoning you had to do was to say X had to be positive, Y had to be positive, which makes sense for an actual fence. And that directly led me to the X less than 10. Okay, so here in our new setting, we had V is equal to XYZ, right? We had Z is equal to 120 minus X minus Y, right? So in terms of what our function is, it's going to be xy times 120 minus x minus y. And now it's just a two-variable calculus problem function. And what's our region? Well, we need x bigger than 0, y bigger than 0, because we're building a physical box, right? Z bigger than 0. But this z bigger than 0 tells me that because z is 120 minus x minus y, that means that 120 minus x minus y has to be bigger than 0. All right. Okay, so there's multiple ways you can think about this, but maybe the easiest is to write it like this. This is equivalent to y is less than or equal to 120 minus x, right? Before I draw this, let me say that gives me my restriction on the other side of y. Or sorry, that gives me a restriction. Let me just draw it. X is bigger than 0, so I'm looking, x bigger than 0, y bigger than 0. So I'm looking in the first quadrant, right? That's what the first two guys tell me. But y is less than 120 minus x. Well, y equals 120 minus x is a line. When x is 0, y is 120. When y is 0, x is 120. So it's a line that goes from here to here, right? I need y less than or equal to that. And so the region of interest for this problem is everything in the first quadrant. So this line actually, sorry, I should extend it. This line looks like that. Y less than this is everything down here, right? But again, we said that we only wanted the first quadrant. So in order to satisfy all those conditions, ultimately, we're interested in this triangular region right there. Okay? That's where x is bigger than 0, y bigger than 0, and y is less than 120 minus x. All right? So that's how you get the regions for these kinds of problems. All right? Okay, I should label this. So this is 120, 120, and of course that's 0. Okay, from here on out, you just do the problem just exactly as we did the previous problem, right? We have our two variable function, v of x comma y equals this business here. We have our region of interest, and so we do step 1, part 2, and part 3. There is no part 3, just like with the previous problem, because everything is nice and differentiable, right? So there's no candidates from places where our function isn't differentiable. Okay. Let's see. Let me actually do the part 1, because I just want to show that these problems can be a little complex, right? So v of x comma y was xy times 120 minus x minus y. V sub x is, let me actually just expand this. 120 xy minus x squared y minus xy squared. So v sub x is 120y minus 2xy minus y squared, which is y times 120 minus 2x minus y. And then v sub y is 120x minus x squared minus 2xy. I've got x's there, so this is x times 120 minus x minus 2y. We want to solve vx equals 0 and vy equals 0 simultaneously, which is y times 120 minus 2x minus y equals 0, x times 120, minus 2x minus y, minus x minus 2y equals 0, okay, simultaneously. All right, the first, let's see, let me call this one A, let me call this one B. A tells me, so you want to be very careful about your algebra, right? A tells me that either y equals 0 or 120 minus 2x minus y equals 0, right? If you forget this y equals 0, you might miss a critical point or miss a candidate point. So you have to remember that, okay? All right. And from here, we can do the algebra in many different ways. Let me do it like this. I'm going to deal with this situation first. If y were 0, then first equation is satisfied. The second equation would become x times 120 minus x minus 2y, that y is 0, equals 0. So that means that x is 0 or x equals 120. All right. So that gives me two candidates, x equals 0, y equals 0, and x equals 120, y equals 0. Okay. Now for the second one, I'm going to hold that for a second. I'm going to look at the equation B. B tells me x times 120 minus x minus 2y equals 0. So either x equals 0 or 120 minus x minus 2y equals 0. Equals 0. All right. If x were 0, then I go back up to my equation 1. If x were 0 here, then y is 120, right? So this means y is equal to 120, and so we get a candidate 0, 120. All right. Okay, And then finally, we go to this last bit here. In this last situation, we have two equations. We have 120 minus x minus 2y equals 0. And we still have that one from equation A. 120 minus 2x minus y equals 0. And so we have to solve 120 minus 2x minus y equals 0. 120 minus x minus 2y equals 0. Solve this system of equations, this linear system of equations. All right. So do this whatever technique you're comfortable with. 2x plus y is equal to 120. X plus 2y is equal to 120. 2 times equation 2, and then subtract equation 1, something like that, right? So I would get 2x plus y equals 120, 2x plus 4y equals 240. Let me subtract the two equations. This tells me 3y is equal to 120, which tells me y is equal to 40. And if y is equal to 40, x has to be what? Well, if I plug in 40 here, 40 times 2 is 80. And if I subtract that to the other side, I'm going to get x equals 40. All right. So my last candidate is 40 comma 40. All right. Oops. So from part 1 of this problem, we actually have a whole bunch of candidates. And again, I wanted to do this just to emphasize, things aren't necessarily just as easy as the previous problem where there was just a single candidate from part 1, right? 0, 0, 120 comma 0, 0 comma 120, and finally 40, 40. Okay. All right. And I'm not going to do any analysis of these at the moment. I'm just going to leave them there. I'm going to think about the boundary. And I'm not really going to do this portion of the problem. But if you wanted to do it, in the most kind of formal, careful way, you do exactly what we did earlier, right, with our first example. However, for this one, I'm just going to notice that this bottom horizontal segment, that corresponds to y equals 0, and so my volume is going to be 0, right? This horizontal line segment corresponds to x equals 0, and so my volume is going to be 0, because again, my volume was x times y times z, right? And then this segment right there actually corresponds to z equals 0. And so my volume is 0. Okay. So even if I did the calculus of those 3 parts, I would realize that everything is actually 0. All right. So we're looking for the maximum possible volume. So obviously it's not going to be 0 because, well, we can easily see that 40 comma 40 is going to be bigger. All right. And in fact, if we did do analysis when we actually did this earlier part, 0, 0 is not going to work because x is 0, y is 0, volume is 0. 120, 0, volume is 0. 0, 120, volume is 0. Okay. And by the way, these cover my 3 endpoints as well. But technically, right, if it was a different problem, you would have to consider 3 endpoints as candidates. All right. Let me actually write them down again. 0, 120, 120, comma 0, 0, comma 0. Okay. But again, all of those end up with volume 0, and so this guy is going to give me my max, right? So 40 comma 40 gives max, right? And we said that z was 120 minus x minus y, which is 120 minus 40 minus 40 in this 40-40 situation. And so that's going to be 40. And so kind of what we expect, the biggest volume is 40 cubed, right? Which is 64000, and let me write it like this, with dimensions 40 by 40 by 40. Okay. All right, so there's our 2 examples. Generally, you're not going to be able to reason yourself out of these kind of boundaries. You're going to have to do the work. So yeah, if you sometimes you're lucky and you don't have you can kind of forego a little bit of the work, but be very, very careful about that. Okay, for example, I could have changed this problem and said I'm only interested in boxes where the y dimension is bigger than 10, or let's say bigger than 60, right? So in that case, my region would change. So let me do this downstairs. So what if only interested in y bigger than 40, right? So maybe we're actually using we're a manufacturer and we want to ship through Amazon, and our product is longer than 40 inches or something, right? So obviously we can't do a 40, 40, 40 box. So how would that change my problem? Well, my triangular region would instead, right? I only interested in y bigger than 40. I would only be interested in, sorry, y bigger than 60, I guess, I think I said. So 60 is here. So I'm only interested in this region up here, right? So in that case, you're probably going to have to work with this part right there, right? You're going to have to do the one variable calculus on that segment because the minimum, or the maximum is actually going to occur somewhere there. All right. And it's not going to be 40, 40 again as it was before because that's outside my region. Okay. All right. So that's actually a nice, very nice modification of the problem where you are forced to do some work on the boundary. All right. Let me say a couple words. So what happens if, so in one variable calculus, if you had to do an optimization problems on an interval that was infinite, right, then how would you do that? Well, you still solve f prime equals 0 for the kind of horizontal bits, place where the tangent line is horizontal. Your endpoints now becomes this endpoint, and then what happens to the right endpoint? You would have to consider what happens where limit x goes to infinity of f of x. All right, and that consideration there will tell you, perhaps there is no minimum because, maybe your function looks like this and it's approaching an asymptote, right? Or perhaps it just goes down to minus infinity, right, as x goes to infinity. But you have to consider that situation. Otherwise, you could be missing a large bit of information about the function. Now, what about now? Well, an equivalent situation would be, let's say, I'm interested in finding the max or min of a two-variable function. Let's say on a whole region. Let's say the first quadrant here, right? Well, the inside, I would do the same thing, find gradient f equals 0. I can work this part by parameterizing, and then I would have to do actually an infinite problem where this is one endpoint, and then the other endpoint would be t goes to infinity. I could work this segment down here where I have to consider, again, endpoint 0, 0, and then t goes to infinity, right, for the other side. But then I also have to consider what happens as I go out in all these different directions, right? So that's a huge problem in practice because, well, there's an infinite number of directions with which we can travel. And any of those directions might be important in terms of the absolute max or mins of my function. So what we're going to do in our class is either we're going to have problems where it's obvious as I go out to infinity, my max or min is not going to be there. Or we're going to see problems where we restrict ourselves to kind of a region which is nice and bounded. All right, so that is, in real life, it's a very, very serious consideration. But because this is the first time we're seeing this material, I'm going to try to restrict ourselves to, again, either where going to infinity means it's obvious that's not what we're looking for, or we're just going to do a fixed bounded region. Okay, and also consideration number 2 is in one variable calculus, if you had a situation like this where, let's say you're interested between a and b, and your function is not continuous, but let's say has an asymptote like that, right? If you only try to consider a gradient, f prime equals 0, you're not going to find the maximum because there's no point here where f prime is 0, right? You have to consider limit x goes to b, f of x. And that will tell you, because that's infinity, that'll tell you there's no maximum, right? So you have to do this analysis at b in order to realize this. Again, the f prime equals 0 is not going to capture it for you. So you have to do some sort of analysis of the endpoint. And if there is a discontinuity or something terrible happening, like an asymptote here, you're going to have to do some sort of analysis with limits, all right? Multivariable, same exact thing, all right? So you can certainly have a function that blows up at certain places, right? So, you know, if I draw something like this, here's my kind of asymptote, and I can just draw, you know, the most simple thing, kind of a very flat thing, and it just goes up to infinity as you get closer and closer to this line, right? You can have the same issue. And in that case, you're going to have to consider a limit. But again, for our class, I'm not gonna do this situation. So if there is some sort of discontinuity or something like that, like this, or like, you know, like the one variable, analogous to one variable situation, it's going to be obvious that's not what we're looking for. All right. Just to keep things simple. But again, in reality, you have to be very careful about this. Okay. All right. So how do we know when we're always safe? If f is continuous on a closed bounded interval, then there is an absolute max min. All right, so this in one variable calculus, this was true. So if we look at a continuous function on an interval, let's say a to b, that's closed and bounded. What that means is my interval is bracket a comma bracket b, right? Including a, including b. Okay, so if it's continuous from a to b, including a, including b, then for sure there's an absolute max or min, right? It could be inside, it could be on the boundaries. Okay, we can see that our previous example up here violates that because our function is not continuous at b. All right, our first one variable situation does not is not covered here because b is infinite, right? So I'm talking about a bounded region, so b cannot be infinite, a cannot be infinite. Okay, so if you're looking at a region like this, including a, including b, if f is continuous on this region, there for sure is an absolute max or min. That was one variable. Two variable, what's the situation? All I have to do is replace interval with region. Okay, so if you are looking at, for example, the problems we just looked at with a triangular region like this, and you're looking at a function which is, you know, well behaved inside this region, f of x comma y equals x squared y cubed plus x to the 10th, whatever, right? No problems in terms of continuity or anything, then we're okay. All right, so that you're definitely going to be able to find a max or min. Okay, and I'm going to try to keep with as much as possible to these kinds of functions in our class. There might be an example or two, especially we'll see in the next section, or maybe in a kind of practical problem where there might be some infinities involved. But again, like I said, it'll be kind of clear that those aren't going to be your answers. But you do have, no matter what, you better say some words about the boundary when you do the problem. Either say, I'm going to do the calculations on the boundary, or the boundary cannot be, the max min cannot be at the boundary because blah, 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 blah. All right? So you better say some words about why you're not considering the boundary if you're not doing any explicit computations. Okay. I guess there's one more word I want to say here before we move on. And that's that what if, so far my two examples, the regions were nice and simple, right? They were just triangular, and I parameterized them really easily because we're very comfortable with parameterizing line segments at this point. But what if my region was more complicated, right? What if my region was a top of a hemisphere, a semicircle, right? What if this was my region? What if my region was something like this? This is y equals x squared, and I'm interested in, let's say, this part, right? Y less than, let's say this is y equals 4, right? Well, same thing, right? You just have to be able to parameterize the region. So here, if this is a circle of radius, let's say radius 3, down here, if I wanted to do the boundary part again, the inside part is the same, right? But the boundary part, this part is just a horizontal line segment, no problem. right? This semicircular part up here, you parameterize using the parameterization of a circle, right? So if this is radius 3 and that's the origin, then you would be perhaps using cosine t comma sine t, right, as our most convenient parameterization. We want the upper semicircle, so t would be between 0 and pi, okay? All right, and for the second region, this top horizontal segment, no problem, just a line segment. We've done a couple of those. This horizontal line segment, same idea. But this curve segment we cover because we're okay with because y equals x squared, so we instantly get a parameterization, right, with t comma t squared. Okay. And since y is 4 is the endpoint up here, so this would be 2 comma 4. We're interested in t between 0, which would be down here at the origin, and less than 2, right, which would give me 2 comma 4. Okay. And again, whatever your function is, you would plug in t for x, t squared for y, and that gives you a one variable calculus problem. All right. What if the boundary was something terrible, right? What if it was something with a terrible equation where you couldn't write it as y equals x? Well, one thing to consider is you might be able to write it as x equals something in terms of y, right? So if your boundary is, for example, x equals y cubed plus 1, then you could use the parameterization where you base it on y, right? So t comma t cubed plus 1, all right? Okay, what if things are more horrible? X squared y plus y cubed x to the 5th equals sine x, right? How are you going to parameterize this? Well, then you're in trouble, okay? So now you're in trouble. And for 15.7, we're not going to be able to do this. 15.8, we might be able to, okay? So we'll talk about that when we get there. But for now, 15.7, you're just going to have to parameterize. Okay, I guess I said that was the last note, but let me do one more note. Sorry about that. F of x comma y comma z. What if we want to optimize this, find the max or min of this, over a region in space, right? Maybe let's say this tetrahedral region, right? Inside this kind of tetrahedron in here is my region, right? Well, gradient f equals 0. We'll find mean candidates on the inside. But what about the boundary? Now, in this case, the boundary consists of 4 parts. You've got the bottom panel down here. You've got the side panel here. You've got another side panel here. And you've got the panel that's facing us right there, right? So you're going to have to do 4 optimization problems on those panels. But those panels also actually live in space. So you're going to have to think about how to convert that problem into 2 variables, right? So that's very, very, very much like our volume of the box problem, right? So you could do it that way. Or alternatively, 15.8 will give us a way to do those panels natively in 3 variables, okay? So if you look at the homework for 15.7, I don't believe, if I remember correctly, I don't believe you'll see any problems like this because it's just horribly, horribly tedious to do it the way that we know how to do it in 15.7. And 15.8, but 15.8 will give us a much better way. Okay. Okay, so I think, so the rest of this section is the second derivative test, but I think I'm going to do that in a second lecture. Because this one's gone. This is an hour and a half, so this has gone a little long. Well, it's not gone long, but it's just a long topic. So I'll do that in a part 2 for this section. Before I quit here, I want to mention optimization is the most important thing that you'll learn in this class, that you'll learn in any calculus class. And so 15.7 and 15.8, they will for sure be on every exam that they're eligible for. So for sure, you will see stuff like this on the first midterm and on the final. All right.